Welcome to the second lecture on derivatives. So, in the last lecture we discussed the concepts of continuity of a function at a point, and also we discussed what do we mean by derivative of the function at a point, and then we saw some properties of derivatives. Today we will first see the relation between continuity and differentiability, and then we will calculate derivative of some more functions. So, the first thing I am going to discuss is there any relation between continuity and differentiability? So, first of all, let us see an example. So, consider the function f of x equal to mod x for x in R. So, let us try to draw the graph of this function. So, f x equal to mod x for any x positive, this is equal to x, and for x negative it is equal to minus x. So, this is also equal to, so f x is equal to x for x greater than equal to 0 and minus x for x less than 0. Right. This is very simple, but useful representation of this function, and the graph looks like this. So, this is f x equal to mod of x. Now, let us ask if the function is, so is f x continuous at x equal to 0. So, here it was easy to draw the graph of this function, and from this graph one can see that the function is continuous at 0, but we can also calculate the limit. So, the limit of f of x. So, to calculate the limit, here it is useful to calculate the left hand and right hand limit. So, if we calculate the right hand limit of f of x, so f of 0 plus h as h goes to 0. What is this? This is equal to limit h going to 0 plus of f of h is mod h, but because we are taking h to be positive, this is same thing as limit of h as h goes to 0 plus, which is equal to 0. Similarly, the left hand limit, limit h going to 0 minus of f of 0 plus h, this is equal to limit of h going to 0 minus of mod h, but here because h is going to 0 minus, mod h is equal to minus h, but h is going to 0. So, minus 0 is also equal to 0. So, limit exists. So, therefore, limit of f of x as x approaches 0, this is equal to 0. Also, f of 0 is mod 0, which is 0. So, therefore, f of 0 is the limit of f of x as x approaches 0, hence f x is continuous at x equal to 0. What about differentiability? Is f x differentiable? At x equal to 0. So, we have to ask this limit, does limit of f of 0 plus h minus f of 0 by h as h goes to 0 exists. So, let us look at what is f of 0 plus h minus f of 0 by h. If we take any h non-zero and look at this difference quotient, this is equal to f of h minus f of 0 by h, and f of h is mod h, f of 0 is 0 divided by h. So, we get mod h by h. Now, we know that mod h is equal to h if h is positive. So, this is equal to 1 if h is positive, and if h is negative, then mod h is equal to minus h. So, minus h by h will give minus 1. So, we see that this difference quotient is equal to constant 1 if h is positive, and it is equal to minus 1 if h is negative. So, therefore, the left hand limit and right hand limit is not equal to right hand limit of f of 0 plus h minus f of 0 divided by h. So, we conclude that hence this limit h going to 0 of f of 0 plus h minus f of 0 divided by h, this does not exist. Which means that the function f of x is not differentiable at x equal to 0. So, what is the conclusion? F of x continuous at x equal to a does not imply that f of x is differentiable at x equal to a. Let me come back to this graph and also explain you geometrically how you can deduce that the function is not differentiable at this point 0. So, we have seen the geometric interpretation that the derivative, if it exists, it is equal to the slope of the tangent line at that point. Now, if you look at the graph of this function, there is no unique tangent line, because for any positive thing you see this is the tangent line, but if x is any negative, then we have this line. So, there is no unique tangent line here, and in fact, you see that the right hand derivative is nothing but slope of this line, which is 1, and left hand derivative is slope of this line, which is minus 1, and they are not equal. So, the function is not differentiable. In general, whenever in the graph of your function, if you see a corner point, then the function will not be differentiable at that point, right. So, continuity, we said that is graphically, it means that you can draw the graph of the function without lifting your pen, and differentiability means that the function should not have any corner, though for complicated functions we cannot just use this interpretation. So, we have to know the rigorous definition also. So, now what about the converse? So, the converse is true. So, the theorem is that if f of x is differentiable at some point x equal to a, then f of x must be continuous at x equal to a. And the proof is very simple. You have to just note this. So, since f of x is differentiable at x equal to a, we have f prime a, which is equal to limit of f of a plus h minus f of a divided by h. This exists, right. Now, to check the continuity of the function, we need to look at the limit of f of x as x approaches a. So, to check the continuity, at x equal to a, we need f of a to be equal to limit of f of x where x approaches a. Now, note that this limit we can also write as limit of f of a plus h where h approaches 0, right. By putting x equal to a plus h, if x approaches a, then h which is equal to, so this is by put x equal to a plus h, that is h is x minus a, and then as x approaches a, h approaches 0. So, we have to check whether this limit f of a plus h as h approaches 0 exists or not, and whether it is equal to f of a. Now, if you see, this is same thing as, so limit f of a plus h, h approaching 0 equal to f of a, this is equivalent to writing limit h going to 0 f of a plus h minus f of a, this is equal to 0, right, because the limit of this constant function f of a as h approaches 0, that is f of a. So, we have this. Now, this is the numerator of the difference quotient in the definition of derivative. So, but for any h not 0, f of a plus h minus f of a, this can be written as h times f of a plus h minus f of a divided by h, right. I just multiplied and divided by h to get this, and what we know is that this limit exists. So, since limit of h as h goes to 0, this is equal to 0, and limit h going to 0 f of a plus h minus f of a by h, this also exists. by the product rule for limits, we have limit of h going to 0 f of a plus h minus f of a. If limit of both the functions exists, then the limit of the product is product of the limit. So, that is equal to 0 times f prime a, which is equal to 0. Hence, f x is continuous at x equal to a. So, what we have seen is that differentiability of a function at a point implies continuity of the function at that point, whereas the continuity need not imply differentiability, that we have seen by a counter example. So, next, to calculate some more derivatives, let us learn what is called product rule for derivatives. So, what this says is that if I take two functions and look at the product, so d by dx of f x times g x, this is equal to f prime x times g x plus f x times g prime x, provided f prime x and g prime x exist. So, we will prove this. So, let us write u of x equal to f x times g x. Then we have to look at, so for any h non-zero, u of x plus h minus u of x divided by h. You have to look at what is this. So, let me write this. This is equal to, u is the product of f and g. So, I get f of x plus h times g of x plus h minus f of x times g of x divided by h. Now, we do just a little algebraic manipulation here. So, we add and subtract, we write this as f of x plus h g of x plus h minus f of x times g of x plus h, and then we again add this same quantity f of x times g of x plus h, and then we have minus f x g x divided by h. So, we write like this and then group the first two terms and the last two terms. Now, if you see in the first two terms, we have g of x plus h is common. So, we got u of x plus h minus u x by h. This is equal to f of x plus h minus f of x divided by h, this times g of x plus h, and then plus in the next two terms we have f x is common. So, I will write f x times g of x plus h minus g of x divided by h. Now, if we look at the two terms on the right hand side, now limit as h goes to 0 of f of x plus h minus f of x divided by h, this we know is equal to f prime x, because f is differentiable at x. What about the second term in this product? Limit of h going to 0 of g of x plus h, this is simply equal to g of x. Why? This is because g is continuous at x, since it is given to be differentiable at x, right. So, note that we are using the theorem that we proved, that if g is differentiable at x, then it is also continuous. So, the limit of this, because as h goes to 0, x plus h approaches x, and because it is continuous at x, this limit must be equal to the value of the function at x. Similarly, the other term, we have limit of h going to 0 g of x plus h minus g of x divided by h, this is equal to g prime of x, and the first term is independent of h, this is f of x. So, that limit is f of x. So, therefore, we have that this limit exists u prime x, which is equal to the limit of h going to 0 u x plus h minus u x divided by h. This is equal to, the first limit here is f prime x, the limit of the second, this is g of x, plus here the first term is simply f of x times the limit of the second one is g prime x, right. So, this is very important formula, and let me, when we derive this formula, let me write as a warning that d by dx of f x times g x, you should not write that this is simply equal to, let me write f prime x times g prime x. This is not true, right. For example, if you take f x equal to g x equal to x, then f prime x is 1, which is equal to g prime x also, but what about f x times g x? But f x times g x is equal to x square. So, d by dx of f x g x is d by dx of x square, which we have seen is equal to 2x. This is not equal to f prime x times g prime x. So, in the beginning many students make this mistake, and when they see product of functions and then limit a derivative, they write as product of the derivative, which is absolutely wrong, right. So, now using this we can derive some more derivatives. So, example, suppose you want f x equal to say x cube, and then find f prime x. So, what we know is that we know derivative of x square and x. So, x cube f of x here is equal to x square times x. Therefore, f prime x will be equal to d by dx of x square times the second function is x plus x square times d by dx of x, which is equal to the first derivative is 2x times x plus x square times 1. So, we get 2x square plus x square, which is 3x square. So, let us calculate the derivative of, to calculate d by dx of x to the n, where n is any natural number. So, one way would be to use the product rule repeatedly to get this derivative, or you can try to calculate the limit directly also. So, let us look at, so we have f x equal to x to the n. So, for h non-zero, if I look at f of x plus h minus f of x divided by h, this is equal to x plus h to the power n minus x to the n divided by h, and if you seen the binomial theorem, then x plus h to the n we can write as x to the n plus n choose 1 x to the n minus 1 times h plus n choose 2 x to the n minus 2 h square, and so on till the last term is h to the n, and then minus x to the n divided by h. Now, here if you note, this x to the n cancels with this, and now you note that every term has h in common. So, we get this is equal to h times n choose 1 is simply n x to the n minus 1 plus we have n choose 2 x to the n minus 2 times h plus other terms which contains h to the n minus 1 divided by h. So, by cancelling this h, we see that every term except this first term contains h. So, this approaches n times x to the n minus 1 as h goes to 0, because all the other terms we get has h or h square. So, they go to 0. So, this proves that, so therefore, d by dx of x to the n is equal to n times x to the n minus 1 for every natural number n. Later we will see that this is in fact true even if n is not a natural number. So, first thing that now from this you can easily calculate d by dx of x square. If you have to calculate, this is 2 times x to the 2 minus 1. So, that is 2x d by dx of x cube is 3 times x to the 3 minus 1, which is 3x square d by dx of x to the 4. So, you bring the exponent down and then reduce the exponent by 1, this is 4x cube and so on. So, remark the above formula for derivative of x to the n actually holds true for any real number n. This will be proved later. But let us try to calculate x to the n for some negative. So, derive the derivative of, we take f of x is equal to 1 by x, then what is f prime x? So, let us do by using our first principle, that is definition of the derivative. So, if we look at f of x plus h minus f of x divided by h, this is equal to 1 by x plus h minus 1 by x divided by h, and then if you simplify this, you get h times x plus h, and then numerator is x minus x plus h. So, here x cancels and we get minus h by h x plus h, and then you can cancel this h, and this is equal to minus 1 by x times x plus h. This is true for any h non-zero, and therefore, the limit as h goes to 0 of f of x plus h minus f of x by h, this is equal to minus 1 by x square, because here in the denominator you see x plus h approaches x plus 0. So, x times x gives x square. This is true for all x not equal to 0. Right. So, this function is not even defined at 0. So, we cannot talk about the derivative at 0, but for any x not equal to 0, we get that d by dx of 1 by x is equal to minus 1 by x square for x not equal to 0. Note that this I can write that this is the same formula for, let me write this agrees with the formula for d by dx of x to the n equal to n x to the n minus 1, or for n equal to minus 1, this will give, this gives d by dx of x to the minus 1 is equal to, n is minus 1 here, times x to the minus 1, which is equal to minus x to the minus 2, which is same as minus 1 by x square. Right. And if you want for other negative exponents, then you can use product rule. So, can use product rule to calculate d by dx of x to the minus 2 or d by dx of x to the minus 3, etc. So, for example, d by dx of x to the minus 2 is same as d by dx of 1 by x times 1 by x, and now you use the product rule. This is same thing as minus 1 by x square, this is the derivative of 1 by x, times the second function is 1 by x, plus the first function 1 by x times the derivative of the second function minus 1 by x square. This is by product rule, and this gives minus 1 by x cube minus 1 by x cube. So, minus 2 by x cube. Of course, this again agrees with the formula that derivative of x to the n is n times x to the n minus 1. Okay, now seeing this, we can derive another formula for we did for product. We can also derive the formula for the quotient of two functions. So, let us try to calculate what is so suppose f of x is differentiable at x equal to a and so then we ask for what about let g of x equal to 1 by f of x. Just like we calculated the derivative of 1 by x, let us try to see if we can calculate the derivative of 1 by f x. So, if you look, I will write what the derivative is that we will get from the proof. So, if I look at g of a plus h minus g of a divided by h, this is equal to 1 by f of a plus h minus 1 by f of a divided by h, and this is equal to f of a minus f of a plus h divided by h times f of a plus h, and this is same thing as negative of f of a plus h minus f of a divided by h. Let us pull this out and then times 1 by f of a times f of a plus h. Now, let us see if the limit exists. Now, what we know is that this limit f of a plus h minus f of a by h, this approaches f prime a, and here I have 1 by f a times f of a plus h. So, this f of a plus h, this approaches f of a. So, what we get is that therefore, the limit g prime a is equal to minus f prime a divided by f of a squared. Of course, here when I am writing g of x equal to 1 by f x, and we are asking for whether this is differentiable at x equal to a. So, g of a must be defined. So, we must have that and f of a is not equal to 0, then g prime a is equal to minus f prime a divided by f of a squared. And then we can derive more general quotient rule. So, this says that if I have f x and g x which are both differentiable at some point and g of a is not equal to 0, then the derivative of the quotient d by dx of f x by g x, this is nothing but the derivative f prime x times g of x minus f of x times g prime x divided by g of x squared. And the proof you can do it by just writing the as limit of the difference quotient, but here note that we have derived the product rule and derived the derivative of reciprocal of function. So, we can use that. So, d by dx of f x by g x, f x by g x I can write as the product f x times 1 by gx, and then the first one by product rule, this is equal to f prime x times d by dx of, let me write it here. So, this is the derivative of the first function times 1 by gx plus f of x times the derivative of the second function d by dx of 1 by gx. This is by the product rule. And then we know what is the derivative d by dx of 1 by gx. So, this is equal to f prime x over g of x plus the second one is plus f x times the derivative is given by minus g prime x divided by g of x squared. Right. And then if you take the common denominator g of x squared, we get f prime x times g of x minus f x times g prime x. Right. So, let us summarize the product rule and the quotient rule. So, the product rule, sometimes we will also write using this notation u v. If these are two functions, then the derivative of u v is u prime times v plus u v prime, and the quotient rule is, if I have u by v, the derivative prime is equal to u prime v minus u v prime divided by v square. This is product rule. And this is the quotient rule. And these rules are very important to calculate derivatives. So, okay, let us calculate some more derivatives. So, one I will do is another example, derivative of say f x equal to square root x. This is defined for all x greater than 0. So, we want to calculate the derivative of this function at any positive x. So, f of x plus h minus f of x by h if x is any positive real number. This we can write as square root of x plus h minus square root of x divided by h. And if x is positive, then for small h, x plus h is also positive. So, we can talk about this square root, and then we want to find the limit of this as h goes to 0. So, while calculating limit, we have calculated limits of this type. So, one way to do this is you multiply and divide by square root x plus h plus square root x by square root x plus h plus square root x, and then what you get in the numerator, you get x plus h minus x divided by h times square root x plus h plus square root x, and then in the numerator x cancels, and then you can cancel the h, you get 1 by square root x plus h plus square root x, which approaches 1 by 2 square root x as h goes to 0. So, what we got is that d by dx of square root x is equal to 1 by 2 square root x for all x greater than 0. Again note that this agrees with the formula of x to the n, because if I write, if we write square root x as x to the power 1/2, then the derivative d by dx of square root x, which is equal to 1 by 2 square root x, which is nothing but 1 by 2 times x to the power negative half, which is same as 1 by 2 times x to the power half minus 1. So, this also agrees with the formula d by dx of x to the n is equal to n times x to the n minus 1. Though we derived this formula only for positive integers, but we have seen that it agrees for n equal to minus 1, it agrees for n equal to square, n equal to half, and later we will see that this is in fact true for any n. Another example I will do is, so far we have only calculated derivatives of some powers of x. So, let us calculate derivative of f x equal to sin x. So, if we look at f of x plus h minus f of x divided by h, this is equal to sin x plus h minus sin x divided by h. And then you recall what is the formula for sin of c minus sin of d. This is equal to 2 times cos of d by 2 okay, sin c minus sin d is equal to 2 times cosine c plus d by 2 times sin c minus d by 2. So, we have sin x plus h minus sin x, this will be equal to 2 cos c plus d is 2x plus h by 2 sin h by 2, and therefore, f x plus h minus f x by h, this is equal to 2 cos 2x plus h by 2 sin h by 2 divided by h, and then we have to ask whether this limit exists. So, this is equal to cos of x plus h by 2 times sin h by 2 divided by h by 2, and now remember that the limit as h goes to 0 of sin h by h is 1. So, therefore, the limit of f x plus h minus f x by h, and the first term cos x plus h by 2, this goes to cos of x times 1. This is because limit of sin h by h as h goes to 0, this is equal to 1. So, therefore, we got that d by dx of sin x is equal to cos x. this is again, this will be useful formula for you. So, then one can ask for the derivative of cos x. Derivative of so again, if you calculate this derivative d by dx of cos x, this will be equal to limit of h going to 0 of cos of x plus h minus cos of x by h. And again, if you use the formula for cos c minus cos d, and then you can show that this limit is equal to minus of sin x. So, this I leave as an exercise. I leave as an exercise for you to check that the derivative of cos x is minus sin x. And now, because we know product rule and quotient rule, we can calculate derivatives of other trigonometric functions. So, what is d by dx of tan x? So, we know that tan x is nothing but sin x by cos x, and then we use quotient rule. So, this is equal to the derivative of sin x times cos x minus sin x times derivative of cos x divided by the denominator is cos x square. This is by the quotient rule. Now, we have calculated derivative of sin x is cos x. So, this is cos x times cos x, and I have asked you to verify that derivative of cos x is minus sin x. So, this is minus sin x divided by cos x square, which we also write as cos square x. So, we get in the numerator cos square x plus sin square x divided by cos square x, but you know that cos square x plus sin square x is 1 by cos square x. So, this is equal to secant square x. So, what we get is derivative of tan x is secant square x. And now, other trigonometric functions also you can calculate, because those are just the reciprocals of these functions. So, if I write d by dx of secant x, then secant x is nothing but 1 by cos x, and then we know the derivative of the reciprocal is given by negative of derivative of cos x divided by cos x square. Right. This is by quotient rule or by our special thing 1 by f x derivative, and then derivative of cos x is minus sin x. So, we get this is sin x divided by cos square x, and this generally we write in this form. So, this I can write as sin x by cos x times 1 by cos x, which is equal to tan x times secant x. So, we will remember this formula as d by dx of secant x is equal to secant x times tan x. Similarly, you verify that d by dx of cosecant x, this is equal to minus of cosecant x times cot x, and d by dx of one more left is cot x, this is equal to minus cosecant square x. So, these two are again exercise for you. So, I will stop here. In the next class, we will learn the chain rule for derivative, which is very useful to calculate derivative of many more functions. Thank you.